A concentrically loaded isolated square footing of size 2 meter by 2 meter carries a concentrated vertical load of 1000 kilonewton. Considering Boussinesq's theory of stress distribution, the maximum depth in meters of the pressure bulb corresponding to 10% of the vertical load intensity will be how much? It should be rounded off to 2 decimal places. So here a concentrically loaded isolated square footing. So the size of the square footing is given, that is, let us draw that. Okay. So 2 meter by 2 meter carries a concentrated vertical load of 1000 kilonewton. Okay, this is 1000 kilonewton. So here if you see in the front view, 2 meters, so this is 1000 kilonewton, and if we convert into the pressure, this 1000 kilonewton, if it is converted into the pressure at the ground level, this is ground level, at the ground level, if Q is 1000 kilonewton, and the intensity can be given by the pressure 2 into 2, it is a square footing, so 250 kilonewton per meter square, so you can write as kPa. So Q as 250 kPa. So this pressure is at ground level. Now, so considering Boussinesq's theory of stress distribution, the maximum depth of the pressure bulb corresponding to 10% of the vertical load intensity. See, this is the vertical load intensity which is said in this question. So 10% of the vertical load intensity. So first of all, we will know what is pressure bulb. So pressure bulb, to give a rough idea of the pressure bulb, if there is any load at the ground, due to this load there will be increment in the vertical stresses all over the point. Yeah, see, due to this load there will be increment in the stresses, vertical stresses. See, already this total soil has in situ stress, where due to this external load there will be increment in vertical stresses at different points, okay. Now considering if you join all the equal increment in vertical stress, all the points where equal increment in vertical stress, you will get a spatial curved surface. So in 2D you can say like that, so which resembles a bulb. See, suppose these are all the points. See, it is a 3D spatial curved surface. In 2D we are only able to see a lemniscate shape. So this is also called as isobar or pressure bulb, which represents equal increment in equal increment in vertical stress. Okay, See here, if you see, suppose due to this Q there is some increment in vertical stress. Let us say this is 5 kilonewton or 5 kPa, let us say. So at this point also, at this depth also, at this distance, it is again 5 kPa, like that. So what is the maximum depth for this increment is exactly under the application of the load. It is only possible exactly under the application of load. This is the line of action of load. So this should be said as the maximum depth in this pressure bulb or in this isobar where equal increment in vertical stress happen. So here, so considering the Boussinesq theory of stress distribution, maximum depth of the pressure bulb 10% of the vertical load intensity. So there will be number of isobars. Okay, each isobar represents one particular percentage increase in this. Let us say we are applying some let us say intensity is Q, small q. Let us say intensity is small q here. Okay, now this pressure bulb may signify some 20% of the Q, this delta Q. Okay, delta sigma. So this delta sigma can represent as 0.5 Q, 50% of the Q, like that. The increment may be some percentage of intensity. So that is given as 10% of the vertical load intensity. Now we will write Boussinesq formula. Boussinesq theory. According to this, increment in the vertical stress is given by 3 by 2 pi 1 by 1 plus r by z whole square power 5:2 into q by z square. So where q is load, z is the depth at which you want to find out this increment in stress, and remaining is, I'll draw, see, let us say this is the load, this is the line of application of the load. Suppose at this point you want to calculate the increment in, so what, so this is z and this one is r. Let me confirm this. You can see this. This one is r, this one is z, vertical distance. So horizontal distance from the line of action of load is r. So now you know all meaning of all terms. So here in the question, if you go back, delta sigma, it is given as 0.1, 10% of the applied load intensity. What is applied load intensity? We have found out 250 kPa. So 250 kPa. So it will be 25 kPa. Sorry. kPa. Now, what is the depth at which delta sigma is 25? The maximum depth. Maximum depth can In a pressure bulb, if you see, the maximum depth can happen only exactly under the line of application of the load at this point. Okay, now sorry for the disturbance. Okay, now we know what is delta sigma, 25, 3 by 2 pi, and 1 plus r is 0. At this point, if you want to find out exactly under the line of application of the load, so this term will become 0, q by z square. What is the q? Q is 1000 kilonewton by z. Z is unknown, which we have to find out. So 25 equal to 3 by 2 pi 1000 divided by z square. 25 40s, 2 20s, then z square equal to 60 by pi, and z is 60 by pi, which is equal to 4.37 meters. Therefore, z equal to 4.37 meters. So this is the answer for the question. Thank you.